After spending hours warding off a wave of cake hounds with your trusted candy cane, you've finally reached the scary red velvet dragon's lair, the final boss of the game. The allure of treasure and sweet treats is too tempting to resist, and so you immediately move your mouse to click start. Hello?
Good afternoon. We've been trying to reach you regarding your car's extended warranty. You should have received a...
How could you forget? The appointment was today. You rush out of the house, leaving the game turned on, leaving Gingerbrave to forever stand in front of the dragon, not budging 1 inch. Poor Gingerbrave. Without the gamer, he can't move.
You may be able to move whenever you want, wherever you want, but the characters in the game require the operations of an external force. This is thanks to vectors and matrices. But what are they exactly? Gingerbrave wonders too in his time waiting for his player to return.
I'm sure we've all played at least one game where we use a joystick to move characters. You tell a character to move up and it does, down, and whoa, you suddenly died. Vectors play a crucial role in this, telling the program which way the player wishes to move. Vectors are simply quantities that have both a magnitude and a direction. The magnitude is the size of the vector, or how far the player wants to go, and the direction is whichever way the vector is applied. This is especially important in video games as these two factors control character movement. Vectors can be 2D, which only consists of x and y dimensions, or 3D, which includes an extra z dimension. For example, a vector at the origin, 0, 0, indicates that the object is at the center of the world. These are position vectors, which simply describe an object's position relative to a point in space. Game designers can also use vectors to represent an object moving from point A to point B, regardless of where they started. These are known as movement vectors. Say a character at a position of 1, 3 has the movement vector 2, 1 applied to it. Its final position will be 3, 4. Notice how the x-coordinate of the final position of the character increases by 2, while the y-coordinate increases by 1. So, the x-component tells us how far the character moves in the horizontal direction, while the y-component tells us the vertical direction.
Now that's not all. Matrices can help transform these vectors. By transform, I mean in their rotation and scaling. These transformations help to simulate realistic movements and perspectives in the game, which is why games are so immersive these days. Think of a matrix as something that's applied to a vector. This is done by multiplying them together. To do so, simply multiply each term in the matrix by the corresponding vector value that appears in the same row. Then add all the values in each row together, which will give us the final vector position. Let's apply this concept to the rotation of a two-dimensional vector. To get the final rotated version, simply multiply it by this rotation matrix. This will rotate the vector counterclockwise around the x-axis by an angle theta. For example, when the following vector is rotated 90 degrees, the final vector becomes so. We get this final value by substituting 90 degrees into the cos and sine functions, and when we add the rows together, we get the final value, and on a graph, the vector has rotated 90 degrees. So whenever you see a character change directions mid-run, it's thanks to these rotations.
Another concept is normal vectors. A normalized vector has a magnitude of exactly 1 while direction is preserved. Normalized vectors are fundamental in video games as they ensure movement speed is constant regardless of the direction. This is especially important in games where players must aim and move accurately. This leads us into 3D video games. You might think they're more complicated, but they use similar concepts as before. The main difference is geometry. In the 3D world, objects are made up of tens of thousands of polygons. These shapes vary from point, lines, planes, and cubes. This is where vectors come back into play. Vectors define 3 dimensions with the addition of z-coordinates, but in 3D objects they also define surface normals, or the direction an object faces. Vectors help define points and orientation in virtual space. Computer graphics use coordinate spaces to place objects in a scene. For example, a 3D model's points are stored in an object space. Then, move to world space where it appears in the scene. This helps in rendering. Rendering is when 3D data is converted into a 2D display onto the screen. Think about how in Minecraft you can increase or decrease the render distance to see farther.
So what happens to Gingerbrave now? Unfortunately, all he can do is wait for his player to return. Perhaps while waiting, he can engage in the staring contest with the giant scary dragon. After all, at the end of the day, you control the game.